Hello, welcome to our latest episode of nanoCHAT PuBCLuB, which is the Ionic Viper video series where members of our community share about their latest publications. I'm Shirley Lynn, and I'm at the U.S. Naval Academy, and I'll let our featured guest introduce himself.
Hi, I'm Kyle Grice. I'm at DePaul University in Chicago.
Thanks, Kyle. So today we're going to be talking about synthesis, characterization, computational studies, and reactivity of platinum-2 complexes of alkyl phosphite ligands, which is an article that you published recently in the Journal of Organometallic Chemistry. And as always, a link to the publication will be found with the description that accompanies this video. So this is not my field at all, like not platinum chemistry. So can you give me some idea of the motivations and context for why you did this study?
Yeah, so I've been interested in platinum chemistry ever since my PhD with Karen Goldberg when she was at University of Washington in Seattle. So we did all platinum chemistry back then, mainly, or I did. There were some other metals in the group. But the goal was to try to break bonds selectively and then oxidize them or functionalize them selectively. And there is some evidence that platinum can do this. And so when I moved to DePaul, I included some work continuing in that area. And so what we're trying to do is figure out how we can selectively functionalize, let's say, alkane bonds, right? Some really strong unreacted bonds. And so this is also nice because these most platinum complexes are pretty darn stable, especially in platinum-2. They're not air sensitive. And so I can work with undergraduates on this project, and it's allows me to teach undergraduates a lot of interesting tools with synthesis, some really cool NMR, and some other tools like X-ray crystallography.
And this is kind of a funny question, but having never done platinum work, is it expensive to buy the metal?
Yes, it is. But thankfully, you can talk to some companies and they'll sometimes cut you a deal. And so I bought 25 grams of potassium tetrachloroplatinate from, I think it was, J&J or Johnson Matthey, but we acknowledge them for cutting us a deal in that paper.
That's nice. That's nice to get a little assistance that way. So take me through some of the major findings that you had in the study.
Yeah, so this paper was actually based on this kind of old paper in the literature. I really love looking back through old literature and finding old papers. And so I have a slide for this, and I'll show you. I found this paper from 1983. It's one of those papers that's still, in a typewriter, looks like it's made on a typewriter. And it was this paper, and it was the group from Shinoda and coworkers. Shoot. There, got it. And so they were able to turn cyclooctane into cyclooctene, which is an alkene, right, using a platinum complex. But the interesting thing was they weren't using phosphines, they were using phosphites, which is still a phosphorus 3, but instead of an R group is an OR group. And so that was interesting to us. And we started to explore that in my group here at DePaul.
So tell us a little bit more about how you framed this to your students to get them interested.
Yeah, so the framing was that we can, try to break these bonds, and in organic chemistry they get taught, you can't really do much except radical chemistry and burning with alkanes. So we can turn something that's, pretty unreactive into something that is a toolbox for organic chemistry. So this was mainly some synthesis and characterization. And so we looked at phosphate ligands because they have some interesting properties. One, they're air stable generally compared to phosphines. Two, they have some back bonding character. As we talk about like carbonyl back bonding in metal carbonyls, but there's actually the same type of thing in metal phosphites. So that could change some reactivity, make the metal more less electron rich, more electrophilic, and that might do something for breaking a CH bond. So that was kind of our hope, and then of course reality sets in. We had previously made some similar ligands, but were aryl phosphites in a previous paper, but they didn't do what we wanted, and so we in this current paper we looked back at these alkyl, not aryl phosphites. And I want to note something here. All this is air stable, so we would use these platinum alkyl starting materials, but they're air stable. It's sensitive to make them because you're using Grignard reagents or alkyl lithiums. Once they're made, they're relatively stable. And so this is what we use to make the complexes and air stable phosphites, and you make an air stable complex. Worked out nicely. Just to show you some of the little small phosphites we were using for this paper that was published, which is these are small, like trimethyl, triethyl, triisopropyl, this tied back one, and then a fluorinated one. And we were able to get some crystal structures, which is great. Get some great NMR data. And then we even got some decomposition. This is an interesting structure where the phosphate has been dealkylated, and this is known chemistry, but I really thought this hydrogen bonding kind of OH split between two oxygens is kind of cool, reminiscent of glyoxime ligands that have been seen on cobalt for hydrogen evolution. And so then we tried to figure out, like, can these things break CH bonds? And unfortunately, they were fairly unreactive. They didn't, and in fact, the isopropyl did break CH bonds by attacking itself. We saw methane in our NMR tube, not deuteromethane, which was our hope to attack the deuterated solvent. And then it actually eliminated propene from the isopropyl groups and decomposed. So didn't do what we wanted, but we learned a lot of you know, information about the structures of these complexes and how the phosphites change it.
One of the things that really impressed me about the article was that you not only did the synthesis and, of course, the NMR, spectroscopy, all the X-ray crystallography, and then you brought computational to this project as well.
Yeah, so I also, that's something that I've learned. I wasn't trained as a computational chemist, but through colleagues here, and then also working with some folks on Viper who know some computational chemistry, or ionic, I was able to learn enough that I was able to start doing it. So I optimized some structures. I did some benchmarking, which is always important. Make sure that your base was set and functional is accurately describing your system. And then I really looked at the metal phosphorus bond, and we found that using a few different ways that actually was a stronger bond than the metal phosphorus bond for the corresponding phosphenes. Like if you sub out one of these oxygens for a CH2, right, you can compare, and it actually is, the phosphite doesn't make a stronger bond, which again points to that back bonding character of phosphites.
Very, very interesting. So tell us a little bit about the people who did this work, because you mentioned that this was done with your students, and we always, enjoy hearing how students progress in research with under the guidance of a faculty mentor.
Yeah, I'll stop sharing there for a second. So yeah, so we had undergraduates and master students here. And so we had undergraduates and master students, various parts of the project. And this goes back way to like 2016 for some of the initial work. But undergraduates were involved in the process, including the synthesis, the NMR, growing crystals, looking at the crystal data when we get it back from our crystallographer. So we don't have a diffractometer here, but we would mail the structures of the crystals out to a crystallographer. So the undergraduates, they learned a lot of these techniques, and saw applications of these techniques. They learned NMR and organic chemistry, and then they could say, hey, I can actually do NMR of these metal complexes and ligands myself. And so it helped reinforce that knowledge, I think, which was good. And then the master students, on the project were also doing some of this with a little more advanced work, and some of the thermolyses and stuff that we did.
Did the master students stay for 2 years or just 1 year?
Yeah, generally they hang around for 2 years.
So. 2 years. That's nice, because then you could really see a whole project go through.
Yeah, and I should also add, for undergraduates, I try to get them in their first year, even before they've taken organic, because I can teach them some of those tools that they will see again in organic. But I think the longer they are working in lab and learning, the better. So I try to get them in their first year.
Fantastic. Well, where would you like to see this work go in the future?
So part of the things we found was that it didn't quite do what we wanted. And so in a way, this kind of not refutes, but it was like making that previous paper we based all this off of a little suspect. So they used, another thing they used that we didn't use in this paper was tin chloride to make tin trichloride ligand. So now the question is, what is that role of that tin trichloride ligand? And does that enable CH activation somehow? And so the next step is we're going to start looking at those tin trichloride ligands on platinum more closely and see what do they do for reactivity, and can they enable CH activation?
Is working with tin Are there some safety concerns you have to put in place
There can be some safety concerns with alkyl tins, but these are kind of tin salts. But so they are toxic, but at a lower, less persistent in the environment, thankfully. So yes, there's always some concerns, but I think that the way we work is generally in sealed J. Young NMR tubes and in sealed containers, and so we'll be safe about it. And the NMRs will be very interesting because tin, I think, is spin active as well, just like phosphorus is. So we already see some platinum phosphorus coupling because one of the isotopes of platinum is spin 1/2. So these huge platinum phosphorus coupling in the phosphorus NMR that's really diagnostic here complex. So we're talking like 5,000 hertz coupling, which is pretty cool. You're used to like proton coupling of a few hertz, right? Tens of hertz maybe. So,
well, that'll be something for us to look forward to, is when you get that tin work done and share with the community. So I just want to thank you for being part of the nanoCHAT Pub Club today, and let all the listeners know that you can actually talk to Kyle through our Discord. So once this is published on our YouTube channel with all the information, you can go look at the paper. And if you have questions for Kyle or just want to, shout out, you could totally do that. And let us know, especially on the Discord or via email, if you'd like to be a guest on nanoCHAT Pub Club. And maybe even Kyle could be the host. He could read your paper and take over this role. So thanks again to everyone for listening in.
Yeah, thanks for the invitation.